Hello students, I thought I would go over an introduction into equilibrium. So what I have here is I have our reactants represented by this cup of water. So I've got about 2/3 of a cup of water in here right now. I colored it blue to try to make it a little easier to see. And then in here I've got some products. Actually, you see there's no products because, as you know, when we start a chemical reaction we don't start with any products. Now, typically, up until this point, we've been talking about the forward reaction, going from the reactants to the products, and talking about how the reactants are starting materials and they make the products. Well, in closed systems, we have what's called reversible reactions, where a reaction can go from the reactants to the products, but because it's a closed system, the products can actually reform and make reactants. And so the reaction can actually go in both ways. And in that case, equilibrium is reached. So that's what I'm trying to mimic here. So I'm going to be passing some reactants and make them into products. At the same time, I'm going to be using a different size spoon to go from the products to the reactants. So I've got a tablespoon to go from the reactants to products. I've got a teaspoon to go from the products to the reactants. So at the same time, I'm going to kind of scoop in here and pour some from the reactants into the products. Now, initially, I'm not going to be able to get much product to turn into reactant. I got just a little bit at that point. I'm going to be able to get most of the reactants to form and make products because I've got a larger forward reaction rate. But as I make more products, I can turn more of the products back into reactants. So you can see that the concentration, the amount of reactants I have is going down, while the concentration of products I have is going up. Now you can see that this is still happening, so we have not reached what we call equilibrium. So right now, just to let you know, I've got about a little over a 1/3 cup of reactant, and I've got about a 1/3 cup of product. But that does not mean equilibrium is reached. I'm going to keep going. I'm going to keep the forward and the reverse reaction going at the same time, trying to turn reactants into products, but then turning products into reactants. And I'm trying to go through the same scooping motion in both cups, moving in to the other cup. See how much I can get. You can see now that I've got more products than I do reactants. Maybe, it's kind of hard to see in the video. So right now I've got about a 1/4 cup of reactant, and I've got about almost a 1/2 cup of product. About. I'm going to keep going and see what I get. I have not changed spoons. My tablespoon is still going from reactants to products. My teaspoon is still going from products to reactants. And keep going in this manner. And then what do you notice about the concentration, the amount of reactants and products as we keep going? We get to a point where the concentration, the amount of each thing, stays the same. So right now I've got a little less than a 1/4 cup of reactant. I've got about a 1/2 cup of product. So the concentration of the reactants is staying the same. The concentration of products is staying the same. The concentration of the reactant is not equal to the concentration of the product. That's not what equilibrium is. Equilibrium means that the forward reaction is happening at the same rate as the reverse reaction. And we have the same concentration, and our concentrations are not changing. So as you can see, I've still got about a 1/4 cup of reactants. I've got about a 1/2 cup of products. The concentrations not equal to each other, but the concentrations are not changing. I've reached equilibrium. All right, so let's take a look at our PowerPoint for this unit. Just gotta share it with you guys. So what I just did downstairs with the cups of water was an introduction into equilibrium. That's what this video is demonstrating as well. If you want to click on this link and watch somebody else do the experiment, that's fine. So what we were using was the 2 measuring cups of water and then a tablespoon and a teaspoon. So the amount of water that was in each of the cups was representing how much of products we had, how much reactants we had, the concentration of each thing. The water that was being transferred represented the rate at which the forward reaction was going and the rate at which the reverse reaction was happening, okay? And as we could see, eventually it got to the point where the concentration of the reactants stayed the same, the concentration of the products stayed the same, and nothing else changed. So equilibrium involves reversible reactions. And reversible reactions are reactions in which it can happen from reactants to products, and then it can happen from products to reactants. So this reaction down here is a good example because it's about the dehydration of copper sulfate. And so here, when you see this, hang on one second, I forgot that this was not plugged in. So when you see this kind of arrow here, this double arrow, that's representing a reversible reaction, where the arrow going to the right, the one labeled endothermic, is the forward reaction. The one pointing to the left is the reverse reaction, the exothermic reaction. So in this case, the reason why they labeled it endothermic and exothermic is because in one case, it's going to take energy. You're going to have to heat up this hydrated copper sulfate in order to form anhydrous copper sulfate. And the good thing about this experiment that I wish we could do if we were at school is that you could actually see the color change of the crystals. So crystals would be blue if we were forming the reactants, they would be white if we were forming the products. Why is this not erasing? So chemical equilibrium, like I said, is when the concentrations of the reactants and the products remain constant. They're not equal to each other. That's a very, very, very common misconception with equilibrium. A lot of times students think that equilibrium is when the concentration of the reactants is equal to the concentration of the products. No, that's not the case. Only if the rates of both are the same. Equilibrium is when the concentration of the reactant remains constant. It doesn't change. The concentration of the products remains constant. It doesn't change. They do not have to be equal to each other. Okay. This graph here is a good example of what's happening with chemical equilibrium. So what we saw downstairs with the water is we started with all of the blue water in the reactant vessel. We start with reactants. We don't start with any products. So in this diagram here, this graph here, we see that we have, oopsie, we have some reactants that we're starting with. So these are going to be our reactants. This red line is going to represent our products because we don't start with any product. And our product is going to increase. The concentration of our products is going to increase up to this point here. The concentration of our reactants is going to decrease to this point here. When they level off, that's when we get to equilibrium because the concentrations of the reactants and the products is not changing. Our next video is going to go over Le Chatelier's principle. So I'm going to stop this one here.